Semiconductor diodes. Semiconductor devices are essential components of modern electronics. In early days of radio and television, transmitting and receiving equipment relied on large, energy-inefficient, expensive, and easily broken glass vacuum tubes. Two key semiconductor devices are diodes and transistors. Diodes are engineered to allow current to flow only in one direction, but not the other. Transistors are used as amplifiers or switches. There are many different diodes with different functions, but they all have two terminals, a cathode and an anode, for current flow. Light-emitting diodes are rapidly replacing traditional lighting sources because of their size, cost, and lifetimes. Transistors were invented at Bell Labs in the 1950s by John Bardeen, Walter Brattain, and William Shockley, for which they won the Nobel Prize in Physics in 1956. They can be used as small devices as shown, a few centimeters in height, or millions of them inside very small integrated circuits, which will be shown on the next slide. Integrated circuits, also known as computer chips, contain thousands of diodes and transistors to replace large electronic components such as resistors and capacitors and vacuum tubes. Integrated circuits are orders of magnitude smaller, cheaper, and more powerful than previous components. Many thousands of diodes and transistors can be placed on a single chip, 1 millimeter by 1 millimeter in dimension. The conductivity of a material in a semiconductor device is controlled by impurity concentrations, which can be varied within wide limits from one region of a device to another. An example is the p-n junction, which is at the boundary of one region of a semiconductor with p-type impurities over here, and another region containing n-type of impurities. Separately, the two semiconductors are neutral. Positive charge carriers, or holes, move in the p-type over here, so the positive guys are going to move. And remember, that's not a real charge, that's a hole. Negative charge carriers, electrons, which are real items, those are real physical items, those are moving in the n-type. When two semiconductors are joined, a few electrons near the junction. Now what's the junction? The junction is where the two semiconductors butt up against each other. So here's the p-type on the left, and here's the n-type semiconductor. This point right here, that's the junction, and that's indicated by that black line there. So what are they doing? Those electrons will diffuse from the n-type into the p-type semiconductor where they fill holes. That forms a depletion region, which is named because the charges and holes are now fixed. And why is that? Well, the n-type now has a positive charge, and the p-type acquires a net negative charge because the electrons moved in that direction. That will create an electric field and an internal electric potential. The electric field points from positive to negative, and it's strong enough so it will stop any more electrons from moving to the left. When a p-n junction is connected to an external battery, here's our battery down here, here's our p-n junction, the current in the circuit will depend on the battery polarity and voltage. For forward bias, the battery is connected with its positive terminal to the p side, and the negative terminal to the n side. The electric field created by the battery, which is in this direction coming out of the battery, and it's in this direction across the depletion region, is opposite the electric field that was created in the depletion region. Because the electric fields oppose each other, the battery voltage decreases the net voltage across the depletion region. Now remember, the original voltage here came by just putting the p and n types together and having electrons migrate over there. So the depletion region will now shrink, and that will increase the conventional current flow. With enough forward bias, this p-n junction looks like a short circuit. Germanium requires 0.3 volts and silicon requires 0.6 volts for current to flow, which then increases exponentially with greater voltage. So by putting on a forward bias here, we can let almost all of this current go through this p-n junction. Now let's switch the battery around. So we have the positive side connected to the n-type. The two electric fields are now directed in the same direction, and the depletion region gets wider, only allowing a small amount of current to flow in the opposite direction. So the current's going to go this way, but only a small amount. This is reverse bias. An electronic device conducting an electric current in one direction is called a diode. A graph of current versus applied voltage for a typical diode is shown right here. So when you have forward bias, your applied voltage, the more you put on, the greater the current goes through that p-n junction. If you use reverse bias, you get a small amount of current flowing in the opposite direction. In a striking contrast to the symmetric behavior of resistors that obey Ohm's law, the p-n junction conducts much more current in the forward bias than the reverse. This over here is a symbol of a diode, and the arrow, or that little triangle there, that points in the direction the current will flow. Reverse current at room temperature is typically a few microamps, and for most practical purposes is negligible. Since a p-n junction diode allows current to flow only in one direction, it can serve as a rectifier. The AC source here applies a voltage across the diode alternately positive and negative. Only during half of each cycle will a current pass through the diode, as well through the resistor. The output voltage shown below is half-wave rectification. So here's the voltage coming out of the AC source, but only when it's flowing in the positive direction will the diode pass a current. So therefore, you're left with these pieces here, which is a half-wave signal. The ones on the bottom are blocked by trying to flow through the diode in the wrong direction. More useful is a full-wave rectifier, which uses two diodes. One over here, one over here. At any given instant, one of the two diodes conducts current to the right, as shown, and then can be picked off the output here. So what happens, here's your AC. When it's going in this direction, it can go through that diode. When it switches direction and goes here, it never gets to this diode because that's going to block it, but the current will flow. So the two of them add together and you get the full amount of current. And this current, with the presence of a capacitor, will convert AC current voltage into DC. Rectifier circuits are very important because many electronic devices, including mobile phones, calculators, and computers, require a DC voltage. The output voltage in the full-wave rectifier is presented by the graphs. This graph here shows the output voltage without the capacitor. The voltage has the same sign, but different values. This isn't really a very practical signal to be used, however. The capacitor opposes the changes in voltage by storing and then releasing charge, and that helps to smooth out the output voltage. So on this point we have the capacitor charging, it discharges, it charges up again, discharges. And so if you tune the circuit correctly, you'll get a more constant DC voltage here. Another useful device is a light-emitting diode, or LED. When a p-n junction is forward biased, a current begins to flow. Electrons cross from the N region to the P region and combine with the holes, like we talked about a few slides ago. The energy equivalent to the band gap can be released in the form of an emitted photon, and what do you get there? You get light. Often, the energy and the wavelength of the emitted photon is in the red region of the visible spectrum. We can see it on LED displays of VCRs, CD players, etc. Infrared LEDs are used in remote controls of TV, VCRs, and stereos. LEDs are also used in home lighting and automobile lights. Photodiodes and solar cells are p-n junctions used in the reverse way. Photons are absorbed in a semiconductor. They create electron-hole pairs if the photon energy is greater than the band gap energy. The created electrons and holes produce an electric current when connected to an external circuit, and this becomes a source of electromotive force and power. It is applied in solar cells, which can power calculators.